So, today we're going to talk about 7-segment displays. I think 7-segment displays are pretty cool. They're really simple as far as displays go, as they essentially aren't more than just a grid of LEDs arranged in a way that you can make numbers out in them. But that also means they're really easy to control and the access you have to them is super direct. As far as how you can interface with them, you've got a couple of options. For one, Adafruit makes this really interesting board they call a backpack board. Essentially, it turns your 7-segment display into an I2C device. So you only have to interface it with 2 wires. The other ones here are just for ground and voltage. That's certainly an option. However, this board is $10 and it only works with certain displays. Plus, you're not really interfacing with the display, rather with this chip here on the back. You don't really know what's going on with the display. Plus, you have to use the Adafruit library, so it's not exactly my favorite solution. Another option I've seen a lot is to use an SAA1064 LED driver IC. However, those parts nowadays are obsolete, so if you want to find that part, you gotta look on eBay, and it's anywhere from $5 to $10, and it only comes in the bulky DIP packages. Ben Eater has a really good video driving one of these displays through combinational logic, and then he condenses all of that into a parallel EEPROM. However, you run into a similar issue because parallel EEPROMs are also pretty obsolete nowadays. So today we're going to look at driving a 7-segment display with an Arduino. And you might scoff at that idea and say it's a total waste of computing power to use a microcontroller just to turn on and off a bunch of LEDs. And you would be right. But guess what? The Arduino chip, that mega chip, is not an obsolete part. You can get it for $2 to $3, and you can get it in this super small surface mount package. So overall, I think it's actually a pretty good option, all things considered. Today I'm going to be using the 5641AS display. It's a cheap display I found on eBay, but certainly you'd be able to apply this concept to other screens pretty easily. To figure out how to wire it up, we'll need to go through the datasheet. And I know that might be a little intimidating because frankly, datasheets scare me too. Thankfully this one is dead simple and we essentially only need 2 things from it. The forward voltage of the LEDs and the pinout for the display. So here we have the pinouts and we'll come back to this, but first we'll find the forward voltage. And we find it right here. As you can see, it's 1.8 volts. We'll need to use this to calculate what resistors we'll need to limit the current. That process isn't super interesting to me, so just know I'm using 330 ohm resistors. So here we have the pinouts for the display. We have different labeling for the different segments. Segments A, B, C, D, E, F, G, and DP. And down here we have A, B, C, D, E, F, G, and DP, and their corresponding pins on the display. And here on top we have pins for the different digits. So what's going on is this is a common cathode display. What that means is that each LED in every digit has a shared cathode and a separate anode. So in order to light up an LED, you connect the common cathode to ground, and then the anode that corresponds to the digit you want to light up to voltage. Manufacturing the display this way allows you to control 32 LEDs with only 12 pins. They call this a matrix, and that's the same way keyboards are wired, so you don't need some kind of super microcontroller with 100 pins or anything like that. So let's go ahead and demonstrate this on the breadboard. Right now I'm connecting 4 resistors to ground to limit the current of the LEDs. Next I'll connect each resistor to the common cathode of each digit. Those are on pin 12, pin 6, pin 8, and pin 9. Next we'll plug in power, although be sure not to plug it in backwards. Now that we have power, we can take a wire from voltage and connect it to the anode of each segment. And as you can see, they light up. And here, if we disconnect the cathode for digit 1, it'll turn off. So let's display the digit 1. In order to do that, we'll need to turn on segment B and segment C. Segment B is already on, and segment C is pin 4. And there, now we have a 1 displayed. One problem you might notice is that there's no way to display different numbers on different digits. We can't have 1 in the first digit and 2 or 3 and so on. That's something we can actually fix once we get it connected to the Arduino. So let's go ahead and disconnect all this and I'll show you how to wire it to the Arduino. Alright, excuse the jump cut, but I'm actually not very elegant when it comes to wiring breadboards on camera. But either way, this is the final result. These white wires at the top and down here connect the common cathodes to our current limiting resistors. These are essentially the wires we'll use to turn on and off individual digits on the display. Then, according to the schematic, I've wired up segments A through DP to digital pin 2 through 9. Then digit 1 is wired to digital pin 10, digit 2 to 11, digit 3 to 12, and digit 4 to 13. And that's all there is to wiring it up. Let's go ahead and connect it to the computer. Be sure to plug in the USB the right way. And now we'll go to the Arduino IDE and we'll write our code. Alright, so now we are in the Arduino IDE, and the first thing we want to do in this code is define all our pins as outputs. We'll also add comments so we know what pin on the Arduino goes to what pin on the display. Digital pin 10 is connected to the common cathode for digit 1 on the display. We'll go ahead and do this for all our common cathodes. And now we can define the pins for the individual segments. Remember that we connected segments A through DP to digital pins 2 through 9. Making sure to organize and comment it like this will make it easy to change what pins correspond to what segments if we ever need to do that. The cool thing about 7-segment displays is that there are only 7, or in this case technically 8, segments. This means we can store the state of the digit as a byte, where each bit will correspond to whether a certain segment is on or not. So let's go ahead and write out some bytes. We'll call our first byte display 1. This is the byte we'll use to store the state of the digit when we want the number 1 to display. In order to display a 1, we'll want segment A to be off. We'll represent that with a 0. We want segment B to be on. We can represent that with a 1. Segment C will also want on. Segment D off. Segment E off. Segment F off. Segment G off. And segment DP off. This byte basically says we want all the segments turned off except for segments B and C, which will give us a 1 on the display. We'll do one more of these together. We can call it display 2. And in order to display a 2, we will want segment A on, segment B on, segment C off, segment D on, segment E on, segment F off, segment G on, and segment DP off. And this is what the rest of the bytes will look like. Don't forget to write a byte for displaying 0. The cool thing is you don't have to stick to numbers. Here we can write a byte for the letter A, and certainly you could do more than just letters and numbers. Since we're storing what segments we want on in bytes, we can also store what digits we want on in bytes, so let's go ahead and create those. We're really only going to use the last 4 bits in these bytes. So for digit 1, we'll want the 5th bit to be 0, because in order to turn on the digit it needs to be low, and we can set the rest of these bits to high. We'll go ahead and set up the rest of our digit bytes. And it's also useful to have a byte that is completely clear. We can call it null. We'll use this to turn digits completely off. Next, we'll need to make some functions. These are basically going to be masks that assign certain bits of our bytes to the actual outputs of our pins. We'll make these functions outside setup and loop. We're going to be calling these multiple times within the loop. So for digital pin 10, we only want to look at the 5th byte. So we'll put a 1 here and leave the rest as zeros. And we'll do that for the rest of these too. We'll make another function just for the different numbers we want to display. Pin 2 is only going to look at the first bit, and pin 3 is only going to look at the second bit, and so on. It's also going to be useful to have a function that clears the display. So we can call it wipe, and inside our wipe function, we'll use the display function we just made and input our null byte to turn all the segments on the display off. And now that we have successfully set up all our functions, we can finally move on to the loop. Let's say we want to display the number 1029. First, we'll start by calling our digit function, and then we'll use the byte we made to represent digit 1. Then we can call our display function and use the byte we made for displaying a 1. Lastly, we'll call our wipe function. Now we can just repeat these steps for every digit. I almost forgot. We need to add a delay to our wipe function. This way it will wait for a while after it writes the first digit before writing to the next one. And our code is pretty much done now, so we can go ahead and upload. And it looks like I forgot to comment these out. But I think that's the last of the errors, so let's try again. And there we go. So we're back at the display, and as you can see, our code is doing something, but it's not quite what we were looking for. I figured out it was because I put the delay function after we cleared the display, when I'm actually supposed to put it before we clear the display. So after I go ahead and fix that, I can upload the code, and as you can see now it looks a lot better. There's still a bit of an issue. We can see all the numbers, but only one of them is being shown at a time, and that's not what we wanted. The solution to this problem is actually to just decrease the delay time in our wipe function. And here's 25. As you can see, it's getting better. Now we'll go ahead and do 10 delay. And we're almost there. You can just barely make out that the screen is refreshing. And if we go all the way down to 1 delay, you can't tell that the display is updating only 1 digit at a time, just because it does it so fast. I'll go ahead and turn the light off so you can see it better. As cool as this is, there's actually some changes we can make to the code to make it infinitely more useful. So let's go back to the Arduino IDE and I can show you how to do that. So we're going to start off here by making some new variables. And we'll just call these value 1, 2, 3, and 4. The next thing we're going to do is define what's called a constant array. We'll call it numbers. Inside the array, we can list out all the bytes we created for different numbers we want to display. A constant array basically just gathers a whole bunch of variables and arranges them so they are accessible through an index number. They're 0 indexed, so the first variable is at index 0. This makes it super useful for us because now we can just use this numbers array and put in a value to grab the corresponding byte for that value. Arrays do need to have defined sizes, so don't forget to put a 10 here. Let's go ahead and give some values to our variables up here. Then we can go to the loop and I can show you how we can apply our array and these variables to the code. You might think we can just put our value 1 variable right here, but that won't work. See, our display function will only work with bytes. That's why we need this numbers array to translate a value into a byte that the screen can actually output. And we can go ahead and do that for the rest of our digits. Now that we're looking up bytes with values, we can actually do math with our values and get them to display on the screen. Here I'm just banging out some quick math that will increment the value of the screen every time the loop runs. This is really just to give you an idea of the kinds of things we can do with our new array. Once we're done, we can hit upload. And it looks like I missed a couple semicolons, but after a few more tries we get a successful. Alright, so now we've changed our project to something that just displays a single number into something that outputs the value of our math functions. The third and fourth digit are pretty hard to read just because of the speed, but you get the point. The really cool thing about this code is that it would be pretty trivial to add I2C functionality to it. That means we can essentially take this circuit and build one of these I2C display backpacks, except it would be simpler because instead of using Adafruit's library, you would only need to send it some numbers. I think that project would be a pretty good follow-up to this video because it would give me the opportunity to show you guys how to take these Atmega chips off the Arduino and integrate them into your own circuits and projects. So let me know if you'd like to see that in a video or any other kind of video you'd want to see. Well, that's the end of the video. If you made it this far, thank you so much for watching. Be sure to like, comment, and subscribe because I have a lot of content planned for this channel. Peace out, and thanks.